Welcome, all of you, to the Math World Academy's SAT Geometry and Trigonometry Masterclass. In this video, we'll learn most important and frequently asked geometry and trigonometry formulas. We've been teaching this test for more than 10 years, and I can tell you right now, the SAT doesn't just test your math skills, it tests your pattern recognition and your test-taking discipline. Today, we are going to break down the exact formulas you need to master the test, and more importantly, I'm going to show you the traps as well. So, let's get started. First up, parallel and transversals lines. When that transversal cuts through, it creates a visual pattern you need to recognize instantly. Remember the letter Z, or N. This is simple. There are total 8 angles. All the acute angles are identical, and all the obtuse angles are identical. That's it. Also, any acute and any obtuse angle will add to 180 degrees. The SAT trap. The biggest trap here is the drawn to scale illusion. SAT will purposely draw an angle that looks like 90 degrees when it's actually 85 degrees. In general, any SAT diagrams are never drawn to scale.
Moving on to polygons, you only need one master formula. Sum of all angles is 180 degrees times n minus 2, where n is the number of sides. Next is triangle congruence. There are 5, and only 5, valid ways to prove two triangles are exactly the same. SSS, SAS, ASA, AAS, and HL for right triangles. The SAT trap. The College Board loves to test you on side-side angle, or SSA. Remember, SSA spells a word we don't say in the classroom, and it is never a valid proof of congruence. Let's talk about similarity. Similarity is all about scale. If you see parallel lines intersecting a triangle, or triangle inside a triangle, or triangles attached to one another, that's your key to know that it's similarity questions. Also, if you see two parallel lines in a triangle, like segment PQ parallel to base BC, you are dealing with the side splitter theorem, where non-parallel sides are split proportionally. Remember, similarity means the angles are identical, but the sides are multiplied by a scale factor. Don't let overlapping triangles confuse you. Just pull them apart, draw it on scratch paper to see the proportions clearly.
All right, let's talk about special right triangles. On the SAT, you're going to see two main types, the 45-45-90 and the 30-60-90. For the 30-60-90 triangle, here is the golden rule. You always want to start with the short leg. That's the side directly opposite the 30-degree angle. Everything scales from there. To get from that short leg to the hypotenuse, you just double it. It's a scale factor of 2. To go from the short leg to the long leg, you multiply by the square root of 3. So commit this to memory. Always anchor yourself to that short leg. Short leg to long leg is times root 3, and short leg to hypotenuse is times 2. Then we have the 45-45-90. This one is actually a lot easier because there is no short or long leg. Both legs are exactly the same length. It's an isosceles right triangle. To find the hypotenuse, all you have to do is take the length of the leg and multiply it by the square root of 2.
All right, let's look at this next slide. This one covers the scaling factor between one-dimensional, two-dimensional, and three-dimensional shapes. Here's the big takeaway. Whenever you're dealing with similar figures, you can actually figure out key features, like perimeter, area, and volume, without ever knowing the exact dimensions of the shapes themselves. Here is how the rule works. If you have a 1D side scale factor of k, meaning the ratio of the corresponding sides is k, then the ratio of their areas is going to be k squared, and the ratio of their volumes will be k cubed. So this whole scale factor concept is a massive shortcut. It allows you to solve for those properties instantly without getting bogged down trying to calculate the actual measurements. That's the main concept you need to lock in here. All right, this slide focuses on triangle area formulas, specifically for equilateral and right triangles. Whenever you come across an equilateral triangle on the SAT, do not waste your time dropping an altitude to find the base and height. All you need to look for is the side length. If you know the side, the area is simply root 3 over 4 times side squared. Having this shortcut is going to be a massive time saver on test day. Now, when you're dealing with a right triangle, the classic 1/2 base times height formula definitely still works, but we want to adjust how we think about it. Since a right triangle has 2 legs, and they inherently act as your base and your height. So the most efficient formula for the area of a right triangle is simply leg 1 times leg 2 divided by 2. All right, next let's talk about SOHCAHTOA. The basic definitions are right here on the slide, but the SAT really wants to test your understanding of the ratios involved, and they love to tie SOHCAHTOA directly into triangle similarity. Here is a massive trap you need to avoid. A sine, cosine, or tangent value does not give you the actual side lengths of the triangle. It strictly represents the ratio of those sides. For example, if a problem states that the sine of an angle is 3 over 4, we know sine is opposite over hypotenuse. But that does not mean the opposite side is exactly 3 and the hypotenuse is exactly 4. It just means the ratio simplifies to 3/4. In reality, the opposite side could be 6 and the hypotenuse could be 8, or any other multiple. All right, next let's look at the complementary angle theorem. This is a massive time saver on the SAT. The rule is simple. If 2 angles are complementary, meaning they add up to 90 degrees, then the sine of one angle equals the cosine of the other. Here is the trick. It works in reverse too. If a test question tells you that sine A equals cosine B, you instantly know that angles A and B must add up to 90 degrees. Next is circle geometry. First, let's understand central and inscribed angle. A central angle is the angle made by the arc with the center, whereas an inscribed angle is the angle made by the arc with any point on the circumference. Note, central angles is same as the arc, and inscribed angles is half the arc. The diameter trap is highly tested. If you see a triangle inscribed inside a circle and one of the sides is the circle's diameter, that triangle is to be a right triangle. The angle opposite the diameter is always exactly 90 degrees. If you spot this, you can immediately pivot to SOHCAHTOA or Pythagorean shortcuts. All right, let's talk about circle arcs and sectors. If your central angle is in degrees, you just treat it as a fraction of the whole circle. For arc length, take that fraction, theta over 360, and multiply it by the full circumference, 2 pi r. For sector area, take that exact same fraction and multiply it by the total area, pi r squared. But here is an SAT pro tip. If the test gives you the angle in radians, do not waste precious time converting it back to degrees. Just use the direct radian formulas. For arc length, it's simply r times theta. For sector area, it's 1/2 r squared theta. Memorize all 4 of these forms. The standard form of a circle is x minus h squared plus y minus k squared equals r squared, where the center is h comma k and the radius is r. All right, let's talk circle equations. 2 huge traps to watch out for here. First, always watch your negative signs in the standard form. Second, remember that the right side of the equation is the radius squared, not the radius itself. If that equation equals 8, your radius is square root of 8. Now, if the SAT gives expanded general form equation at you, do not waste your time manually completing the square. Type it exactly as is into your built-in Desmos calculator. Look at the visual graph to instantly extract your center coordinates and diameter and solve the problem. This is altitude-hypotenuse theorem. It's not the most common concept on the SAT, but when they do test it, it is a massive time saver. Anytime you see a perpendicular altitude dropped right from the 90-degree angle onto the hypotenuse, use the geometric mean formulas right here on this slide. Applying these relationships will help you completely bypass all that messy Pythagorean math. All right, let's wrap up with radian conversion and the unit circle. The main formula is pi radians equals 180 degrees. You can use that simple proportion to easily convert back and forth. Now, the entire unit circle isn't heavily tested, but you might need to know the positive and negative signs for each quadrant. Just remember the acronym ASTC. All students take calculus. Quadrant 1, all trig functions are positive. Quadrant 2,
only sine is positive. Quadrant 3, only tangent is positive. Quadrant 4, only cosine is positive. Lock that acronym in your memory and you will be ready for those coordinate geometry trig questions. So that's it. These were major geometry and trigonometry concepts you need to know. If you master these, you are up for the success in SAT test. If you have any questions, feel free to text at 919-885-0591 or email at info@mathworldacademy.us. Thanks for watching. See you in the next video.